Okay, welcome back. I'd like to talk to you now about something called sensory adaptation. So it turns out that if you look at something continuously, eventually it kind of disappears. Turns out that the receptors in our eyes, in our ears, in our skin, in our taste buds, in our mouths, like change. That's what they're really sensitive to. So there's something called sensory adaptation. When a stimulus does not change, we respond less to it. So I've got a couple of illustrations of that here. The first one is a pair of pictures from a famous researcher called Yarbus, where he had participants look at other people and he tracked what they looked at. So as their eyes moved, where did they fixate? Where did they focus their attention? Where did they really look? And you can see that when you're talking to somebody, your eyes are moving all the time. So each of those little dots and lines in there shows you where the eye was fixated, where the person was looking. So we're always looking around at images. We don't stare directly at them because the receptors in the back of our eyes, which we'll talk about in the next lecture, if you stimulate them in exactly the same way for an extended period of time, eventually they stop responding. Think about a firefighting truck. It has a sound. Wow, wow, wow. Well, it depends on the country what the sound is. They have a sound and they have flashing lights. So you have both visual and auditory signals that are constantly changing. And the reason that fire trucks and emergency medical technicians ride in vehicles where the stimulus is changing, either visually or auditorily, it's both, is because people pay more attention to those sorts of stimuli, because if it was just or just a bright light that didn't move, eventually people stop responding to it, and eventually it doesn't actually take very long. Think about kissing. That's another example. If somebody kissed you and just put their lips up against you and never moved, it wouldn't be much of a kiss. And eventually, after a few seconds, you wouldn't feel anything at all. Kisses involve movement. Why is our ability to detect something depend on whether that thing is changing in some way? Because we are designed to survive, and new stimuli, new things, novelty is really important to us. And so our systems are designed to pay attention to novel, changing things, not to steady state, unchanging things. So what are the repercussions of that? Well, a lot of people, like me, have to wear glasses, and sometimes you see, I'll pick on professors, sometimes you see professors walking around with glasses that are just filthy. It's like, how can anybody see through those glasses? Well, the dirt is always there. We don't notice it. It accumulates constantly, and it doesn't change. It's always there, so we don't notice it. Another example is if you've ever walked into the home of a friend, maybe they have cats and a really smelly litter box, and you think, oh my God, it stinks in here. Maybe it's old laundry. Oh, it smells. How can they live in this stinking place? It's because they don't smell it after a while. Their systems, their sensory systems, adapt. It's unchanging, so the system just starts to act like it's not there at all. That's why detection is so tricky. Okay, when we're talking about the visual system, the thing that we detect is light. So let's start with the question of what is light? It turns out that light is a funny thing. There's a kind of energy that's all around us. It's called electromagnetic energy. And electromagnetic energy is the stuff that runs microwaves, ovens. It's the stuff that radio signals are sent around. It's the stuff that allows us to take x-rays. It's all the same stuff. That energy, what differentiates radio waves from microwaves, from ultraviolet light and x-rays, is wavelength. What's the distance between two peaks of two waves? I live in Southern California, so what I can do is go to the beach and look at the distance between waves. If waves are one right after the other, the distance is very small, then I would say that's a small wavelength. Sometimes the ocean is very relaxed and a wave will go by, and then maybe I have to wait 5 or 10 seconds, and then the next wave will go by. So there's a lot of distance between the waves. Those would be long wavelengths. Light is simply electromagnetic energy that has a wavelength somewhere between 400 nanometers and 700 nanometers. That's it. It's the same stuff as X-rays and microwaves. There's nothing special about it, except we have cells in our eyeballs that respond to it. So there's nothing special about light out there in the actual world. What's special about light is that, what defines light, is that we have cells in the back of our eyes that respond to it. Okay, so between 400 and 700 nanometers, there are a lot of different wavelengths, and it turns out we experience different wavelengths as different colors. So if something's a short wavelength, then we might experience it as sort of a blue or maybe purple. And if it has a long wavelength, then we might experience that thing as red or orange. If you ever want to remember the order in which colors correspond to different wavelengths, there's a mnemonic called Roy G. Biv. A person's name, right? My old buddy Roy. But what Roy G. Biv reduces down to is red, R, O, orange, Y, yellow, G, green, blue, B, indigo, I, and V is violet. The funny thing about light is that we experience these colors, but the electromagnetic energy does not have those colors. Color is something we construct in our brains. Now, a lot of times in the buildings we're in, or right now as I've got these lights on me while I'm recording, the light appears to be white. And back in the 1700s, a fellow by the name of Isaac Newton discovered that if you take regular old light, like the light that's outside or the light that's in this room, and you shoot it through a prism, what the prism does is it bends the light differently depending on its wavelength. So if you take white light and shoot it through a prism, what you'll see is a rainbow, right? So all the light that's out there in the world contains more or less of all the different wavelengths that your eye is responsive to. Okay, come right back and we'll talk about the parts of the eyeball and some really interesting stuff.